All right, so modern roller coasters have vertical loops like the one that's shown. The radius of curvature is smaller at the top than on the sides, so that the downward centripetal acceleration at the top will be greater than the acceleration due to gravity, keeping the passengers pressed firmly into their seats. What is the speed of the roller coaster at the top of the loop if the radius of curvature is 15 meters and the downward acceleration of the cars is 1.5 Gs? So 1.5 times 9.8. Well, let's just remind ourselves, if I have a vertical loop, there are two forces acting when I'm at the tippy top of that loop. First, I have the force of gravity, and we know that's between the earth and the car. So we're going to put car on the top because we're interested in the forces on the car. So that one goes on the top of our tree and the earth. And we know that that points down. We also have that track interacting. That's a normal force, so the force of the seat on the passengers. If we think of it all together, we're going to call that a normal force. And that's between the car and the track. And that's pointing down. And we're told that that force is equal to, that's also pointing down. We're just going to say that that's pointing down also. All right, I'm just going to get a picture there. Okay, two forces pointing in the downward direction. Well, if it's in a vertical circle, the acceleration, the centripetal acceleration, is also in that downward direction. And we are told that the downward acceleration, the centripetal acceleration, is 1.5 times G. So, what is the speed, it asks, of the roller coaster at the top of the radius of curvature? At that top. So we know the centripetal acceleration is v squared over r. So that means that we have 1.5 times g, which is 1.5 times 9.8. That equals 14.7 meters per second squared. So I have 14.7 is equal to v squared over the radius, and I'm told that that radius is 15 meters. So if I multiply both sides by 15, take the square root, I find that my speed at the top is 14.8 meters per second. So recognizing that at the top of the loop, all the forces are in the downward direction, it's kind of fun just to rethink about what those forces must be related to. We know that the centripetal acceleration on that person is 1.5 times g. That's given in the problem. So we know that's 14.7 meters per second, and that has to be related to the speed in our relationship for centripetal acceleration. So pretty straightforward problem, but really kind of thinking about how those forces interact with each other at the top of that roller coaster. All right, good job.